Okay, so good evening everyone. Uh, Today is the lecture 3 of the NPTEL course Algebra 1 NOC 67, and as per the syllabus, uh, today we will be doing some group action and problem related to group actions, and maybe little bit of Shiloh theorem if our time permits. So let's start with problem 1, lecture 3. So let's start with problem 1. Okay, let G be a group and and
Hello.
hello.
Hello, you're starting straight away with problems, or like you will go over the
Actually,
concept?
I contacted with the team, and I uh, they told me to do assignment problems only. I mean problems related to assignments, and if you need to revise the lectures, you need to uh, like see them. It's not my duty to revise
Okay,
for you.
okay, okay. That's thank you. And one more thing, like the notes for this week, they are not up. Whom should I contact to get them up?
Yeah, I
Uh,
mean there will be a mail address for help. You should mail directly. I
okay,
think it will be uploaded soon, and if not, maybe wait 1 or 2 days and then mail them.
okay. But the assignment submission deadline is tomorrow, right? Like I cannot.
Okay. Then I think you should start the like viewing the lectures like.
Okay, okay. Yeah,
Mm-hmm.
yeah, yeah, that I like that I'll do. Uh,
Mm-hmm.
and one slight problem, will you deal with our single problem in assignment too? Because I think the
No, no,
solution.
no. I cannot do assignment problems. They will like give me warning then.
No, no, no. Assignment number two, like assignment number two, I think one solution is wrong. I have put it in the
Okay,
forum,
okay,
forum also, and they are not. Nobody is replying, and I was
okay.
wondering,
Then you
you are there to reply, or like you are.
no, no, no. I mean, I am not in the group. They forgot me to add there. Okay,
Okay.
this is my mail address. You can just send me a mail after the class.
Okay, okay.
Ha ha.
So whom should I, because if I'm not getting any reply on the forum, whom should I contact? Like again NPTEL
Maybe
persons.
you should directly contact the course instructor. I mean, you will
Oh,
get their mail address in their websites.
okay,
Like,
okay, okay.
ha ha.
Thank you.
Ha
I
ha.
won't take.
Yeah,
Okay,
yeah, yeah. Okay.
yeah.
Okay. So we come back to our problem. Uh, so yeah, let G be a group and A be a non-empty set. Mm. So now, yeah, let G acts on A, and I hope you are familiar with the group action right by now. That is like, uh, okay, I'll just write. So G acts on A means uh, G dot A should belong to A for every G belongs to G, and for every A belongs to A, and by G dot A is a, I mean small g acts on small a such that uh, one of G dot A should be A, and this should hold, and yeah, this should hold. So yeah, I'll be doing this. Yeah. Let G act on A and prove that yeah, sure, I can understand. Yeah, yeah. The prove that if AB belongs to A and B equals to G dot A for some G belongs to G, then uh, stabilizer of G of B to G of stabilizer G of A, G inverse. And by stabilizer of G of B, by that I mean that all the elements of G such that G dot B equals to B. I'm defining this via left action. One can simply imitate the definition for the right action too. And okay, maybe we should do it first. Then we will do another one, that is if the action is transitive, then uh, if the action is transitive, then the kernel of the action, that is the all the fixed elements of all the elements of G for which the action is fixed is intersection of the all the stabilizers. Okay, so maybe we should start with this solution. Uh, so we'll prove the forward direction first, that is if X belongs to stabilizer of G of B, then we have that X dot B equals to B. Now G inverse xg dot A equals to G inverse X dot B, right? Now this means G inverse B, because, and this is happening because of this, which is nothing but which is nothing but G inverse of GA, which is A. So we have G inverse xg belongs to measure of G of A. I hope this is clear, right? Because this is acting on A and you are getting A, so this belongs to the stabilizer of A in G. Hence the forward direction, that is I mean X belongs to G of step GA, G inverse, right? Because from this line this follows. Now for the inverse direction we have that let x belongs to g of step g a of g inverse. Then we have g x g inverse dot b should be g x of g inverse g a, and it should be gx dot a, and again it should be ga because x is coming from this your g stab g a g inverse, and it should be b, so that gx g inverse belongs to step g of b, because again you see that product of this with b should be b, hence we have g so what we are trying to do was this belongs to this. Now yeah, I am making a mistake. Can anyone tell me what mistake I did? I mean, simply if we try another way, that is x belongs to g stab g a g inverse, and if we take x equals to g x1 g inverse, where your x1 belongs to stab g a, then now if you put x dot b, then it should be g x1 g inverse d, and your g inverse b is a, and x1 dot a should be a because x1 coming from step ga, then it should be ga, and ga is b. Yeah, so I should erase this part. Let this, so x equals to g x1 g inverse, where g1 x1 belongs to step ga. Then we have x dot b should be G x1 G inverse B, which is nothing but gx1 dot A, and x1 belongs to stab GA, then it should be GA, and GA is nothing but B. So what we have seen that x belongs to stab GB, hence we are done. Now coming back to our next problem, that is deduce that if G acts transitively on A, then the kernel K of the action is intersection G running from small g coming from capital G and G stab GA G inverse. So the kernel of the action is nothing but like if G acts on A, then the kernel of the action should be G of G such that G of A equals to A for all A belongs to A. So I should probably put this here. Now we'll come to the solution, but before that maybe you should try for 1 or 2 minutes, then tell me. আজকে স্টুডেন্ট বেশি নেই, একটা এসেছিল তার বলে আমাকে রিভাইজ করিয়ে দিতে, এখন আমার তো কাজ রিভাইজ করানো নয়। তা তুমি যদি রিভাইজ করতে হয় তুমি লেকচার শোনো। ও হচ্ছে একটা কোনো ওই অফিসে কাজ করে, বুঝলে তো, বুড়ো আর কি। ও চলে গেল, বললাম যেহেতু পড়িনি আমি চলে আসছি। আর একটা মেয়ে এসেছিল, ও চলে গেল। আরে ক্লাস না করলে বোঝা চাপ আছে, এত ভরে পড়েনি। আর এবার তো ধীরে ধীরে কঠিন হওয়া স্টার্ট হয়েছে। সাইলো থিওরাম থার্ড লেকচারেই সাইলো থিওরাম গ্রুপ অ্যাকশন ঢুকে গেছে। ঠিক আছে, যত কম অ্যাটেন্ড করে। ওকে, let us start doing this. So first we will see what this means. This means G acts transitively on A. This means for all A, B belongs to A, there exists small g belongs to capital G such that B equals to G dot A. That means what you are saying that for every two elements of A, we can go from one element to other via a group action. So we need to show that this kernel that we define via this uh, is nothing but uh, all the conjugates of stabilizer of a single element. So it is quite interesting if you see, because A is random here, so no matter what A you choose, you can always recover your K. Okay, so first we do again the forward direction. Let x belongs to K, then x dot A equals to A for all A belongs to A. Which we just defined here. Let G belongs to G, then we have that G inverse G xg dot A, G inverse dot x G dot A, and which is G inverse of G dot A, right? Because x belongs to kernel, so this follows, and which is nothing but G inverse of G dot A equals to A. So we have G inverse xg belongs to stabilizer of GA for all small g belongs to capital G. Thus we have x belongs to G stab G A G inverse for all small g belongs to capital G. Hence we have small x belongs to G, small g stab G A G inverse. So forward direction is clear, right? Now we will be doing the inverse direction. Let x belongs to intersection of G stab G A G inverse. Let B belongs to capital A. So now we will use the transitivity of the action, because the action of G on A is transitive we have b equals to h dot a for some h belongs to g. Now x equals to hy h inverse for some y belongs to step ga, because x is coming from there. Thus x dot b equals to hy h inverse dot b equals to hy dot a, it's nothing but h dot a b. So we have that. So we have that x stabilizes b. Now b was arbitrary, right? Since b of a was arbitrary, so x belongs to k, because you see that x dot b equals to b for all small b of a, so x belongs to kernel by our definition. So this was an interesting problem, right? Now we can move on to our third problem. So this is just the follow-up of what we did till now. More of you can say that real life problem, because we will be using permutation group. Okay, let G be a permutation group on the set A. This means that is G is a subgroup of SA. SA is the mother permutation group of A, and A is finite. That means that SA has order like number of elements of A combinations. So yeah, let sigma belongs to G and let small a belongs to capital A. Now we have to prove that sigma stabilizer G of A sigma inverse equals to stabilizer G of sigma A. Deduce that. Okay, maybe again we'll do the next part in the next problem. We should keep the solutions smaller so that it remains interesting, or otherwise people will get bored. So maybe try for 2 or 3 minutes, then we can start discussing. Okay. So let's start with the forward direction, that is let x belongs to sigma stabilizer g of a sigma inverse. Then we have that x equals to sigma y sigma inverse for some y belongs to stabilizer g of a. Now our aim is to show that x belongs to this, so we will directly compute x dot sigma of a, which is nothing but sigma y sigma inverse, and from this part this is nothing but sigma dot a, so it should be sigma y dot a, and y already belongs to stab g of a, so y dot a should be a, which is nothing but sigma of a, and that is sigma a. So we have sigma stab g of a or sigma inverse belongs to, is a subset of stab g of sigma n. Now for the other direction, one can similarly follow these steps and going backwards, follow these steps and find the solution, but for the sake of completeness we will do this. Let x belongs to stabilizer g of sigma n. Then we have that okay, so try to compute this directly. Sigma inverse x dot sigma dot a. Let's see what happens with these things. So sigma inverse x of sigma of a, it should be sigma inverse sigma of a, which is nothing but sigma inverse sigma dot a. This is a. So we have sigma inverse x dot sigma belongs to stab g of a. So this implies x belongs to sigma stab g of a to sigma inverse. So we are done, right? Now we'll go to our next problem, which is nothing but the follow-up that I just said, question 4. Deduce that if G acts transitively on A, then intersection sigma of G, sigma step G of A, sigma inverse equals to 1. So what we can try showing that the kernel what we said earlier is 1. But so can you show that how can we show that the kernel should be identity? And your G is here nothing but G is a subset of this. And one thing to remember that G acts on A. By this we simply mean that there is a group homomorphism from G to S. So I hope this already you know. So this is quite interesting from coming from the definitions of group action, that when you have a action of G on a finite set A, that means you are giving a group homomorphism from G to S, and in action what we defined as kernel, here it is simply the kernel of the group homomorphism. That's all. But I am not going into this detail because this is coming from the standard textbook syllabus. I mean any book you follow from group action, or maybe your professor's lectures, then you will see that it is there. Nothing really non-trivial here. So maybe using this you can try for 3 or 4 minutes. It's not that hard. Then again we will discuss this. And I need to take break for 1 to 2 minutes because this is a long class, and as there is no conversation between us, so to save my voice I need to take 1-2 minutes break. Humphreys, আলাদাই দিচ্ছিস তো? ওই যেটাই কাজ করছি ওটাই লাগছে। পেদেই যা, জীবনে পাদা ছাড়া আছে আমার না শুধু ঘুম পাচ্ছে আর পড়াটা আজকে ভালো লাগছে না। যেহেতু চকলেট হয়েছে কি খাবো না, কাটটা মুখে দিয়ে
পারবো না বললাম।
আচ্ছা দিদিদের ওই চকলেটটা গেছে রে এখনো? তোরা মুখে বলে দিলে এখনই আমি বলবো সোজা। So let's start doing this. That is, if G acts transitively on A, then this should be 1. So using this solution, that is, or this thing, this question 2, we can we will directly use this, right? So as G acts transitively on A, so the you can simply just write this step G of A sigma inverse equals to K, and K is nothing but the kernel of this kernel of group homomorphism, right? Now this is actually one liner problem. So now we have G to SA map, right? A group homomorphism, and we already have G is a subset of SA, so I mean then it is clear that this map is homomorphism, right? I mean, how? Because from the isomorphism theorems, so you can check that. So kernel equals to the identity element. So we are done. Next, we go to an interesting problem. Suppose G is a subgroup of SA which is abelian, that means commutative, and transitive subgroup. That means G as a group acts on A which is transitive action, so that sigma of A not equals to A for all sigma not equals to 1 in G and all A belongs to A. And from here deduce that the cardinality of G should be cardinality of A. So more or less we started with A as finite, And so SA is finite, that is permutation group of number of elements of A. So as SA is finite, so without a doubt G is also finite. So we can talk about the cardinality of G. So from here we know that our question is standard. So maybe we should try solving this one. Again, take 2 or 3 minutes and just tell me. থ্যাংকস। ওয়েট করছিলি এছাড়া যে কী করবো আমি, অ্যাকচুয়ালি আমার মাথা যন্ত্রণা কমে গেছে। হুম, কাজ দেয় না।
বেশি খাবি না, মাইগ্রেন হয়ে যাবে।
একটু বেলা না হ্যাঁ, ঘাড়ের কাজটা এরকম করে টেপ দুশো দিল।
মন দে।
অনেক প্রবলেম আছে, 1 ঘন্টা আরামে কাটিয়ে দেবো। হাগে না খালি এখানে সে পাবে। চুপ, শুরু করবো। So as I have already told that by transitive subgroup, okay, I should write it down. By transitive subgroup, we mean that action of G on A is transitive. So, and from this what we will see that for each small a belongs to capital A, we have kernel is 1, that means intersection of sigma of G, sigma stab G of A, sigma inverse, which is nothing but sigma of G, sigma inverse stab of A. Now you are wondering why is this happening? Because I started with G abelian, right? So that is why this is happening. Stab of GA, nothing but stab of A. since G is abelian. Because stab of A is equal for every sigma, and and this term is common in every single term is stab GA. So from there we have this. So for all small a belongs to capital A and sigma not equals to 1, we have sigma of A not equals to A. So I think we have shown our first to-do list. Now for the second part, second objective, that is we have to show that the cardinality of G equals to cardinality of A. So from here we can just start, because the action of G is transitive if we fix small a from capital A, then for every small b belongs to capital A, there exists sigma from capital A such that not capital A, this should be G, capital G, such that B equals to sigma of A. Suppose now that sigma dot A equals to tau dot A, where your tau and sigma both are sigma and tau both are coming from G. Then tau inverse sigma dot A is A, right? So that tau inverse sigma belongs to stabilizer of A, which is nothing but 1. Hence tau inverse sigma is identity of G, which implies that tau equals to sigma. So this means, thus we can say for a fixed small a belongs to capital A, that for every small b belongs to capital A, there exists a unique sigma belongs to capital G such that sigma dot A equals to B. in this way we define an injective mapping phi of A from A to G. Hence, I mean, from this it is clear, right? Because the map is injective, so uh, I mean the image of phi A of capital A is isomorphic to A, so their cardinality is same, and the image of phi A sits inside G, so from there this is true. Now for the converse part, now with small a from capital A fixed, we define of A G to A by psi of A sigma dot A. But this mapping is injective, right? What we have seen from earlier. Okay, let me write it down. This mapping is injective since if sigma dot A equals to tau dot A, we have tau inverse sigma belongs to step GA, which is 1, and from there it is clear. So we have this, and this implies that this. So we are done with this problem. The problem was, suppose G is a subgroup of permutation group of A, which is abelian and is a transitive subgroup, and by transitive subgroup we mean that the action of G on A is transitive, and so that sigma dot A not equals to A for non-trivial sigma and not for all A, and from here we deduce that this is true. Now we go to our next problem. Okay.
Good evening, sir.
Yeah. Yes.
Sir, I have joined a little late.
Okay.
Can you please explain me what you are discussing today?
Okay. So the syllabus was group action and Silo theorem, but Silo theorem part was like only preliminary things were done, like the definition and one or two properties. So I thought maybe I would do mostly uh, group action problems and maybe last one or two problems from Silo theorems. So we are
Okay.
actually following the exercise from Gamit foot. So yeah, from
The
there,
chapter number?
chapter number, let me tell you it. I think there is a specific section Silos theorem 4.5, and maybe chapter number 4 you can from
Sir,
group,
for group action?
yeah, group action, yeah.
Okay, okay,
So from there I picked some problems. Uh, I mean, which are doable in a live class. I mean,
okay, okay.
uh, where the possibility of me doing wrong in calculative parts. So yeah.
Okay, sir.
Hmm. So for our next problem, wait. Uh-huh. Yeah, should be question number 6. Prove that if a subgroup H has finite index in a group capital G, then there exists a normal subgroup K such that this notation simply means that K is normal in G such that K is a subgroup of H and the order of uh, K in G is less than factorial n. So this comes from little bit of counting problem, and again we will be using mainly group action. So it will be interesting if you can try yourself and let me know. And after that we will be doing some uh, conjugacy class related problems. I hope you are already familiar with this. Okay. Great. এই লোকজন জয়েন করে গেছে, আবার কোশ্চেন করা স্টার্ট করে দিয়েছে। একদম ভালো লাগে না আমার। আচ্ছা, আমরা তো শান্তিতে পড়াচ্ছিলাম না এই জন্য। হ্যাঁ, ভালো লাগছে না একটু? ওয়াইফস না, ওয়াইফ আর ওই বড়গুলো। আর 7টা 6 বাজে সবে পড়াচ্ছে। বলে এখানে তো শান্তি আছে, শান্তিরা সব শান্তির ছেলে হয়ে গেছে।
ও না আমার সামনে বসে চিৎকার করছে, ওর একটু মানে ইয়েও হচ্ছে না যে পাশে একটা লোক করছে। সব
জোর ছেড়েছিস মনে আছে।
ছাড়িনি তো, মেসেজ করছে।
ওকে। So if one of you have any doubt, please let me know. Also, I have seen that you guys were discussing in that group you have created, which is very good.
Yes, sir.
Yeah, uh, I could not reply in time, but I see that one of you asked question and another one replied. So which is
Yes, sir. Sandeep asked some questions, but At the end, he told me
Ha ha ha.
that he did not find the group much effective, and he left the group.
Okay, okay, it's fine, it's fine. Because this is not really. I mean, the class and the people are not focused for that purpose, right?
Yes, sir.
Yeah, 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 yeah. I can understand that. Yeah. Okay. Okay. I shall start doing this. Uh, so one thing is clear that if we are given a group G and if H is a subgroup, uh, then H can act on G by H by, you can say, by left multiplication or right quotient or left quotient, right? Because small g can act on uh, g g g dash h, and they can act like this g g dash h. So yeah, uh, now I shall write this formally. G acts on the quotients g by h by left multiplication. Let lambda from G to permutation group of uh, G by H, and you know that G mod H is finite, right? Because it has finite index. So as a set it is finite set. So when we talk about the permutation group of n number of elements, so it is possible. And also you can see that as G acts on the quotients G by G mod H, so we can simply have an equivalent notion of group homomorphism from here. I mean, if you are given a group action map, then by equivalently you can say that you have a group homomorphism from G to permutation group. Yeah. Uh, and please let me know if you need further understanding of this, because this is very crucial part of the group action. Induced action. And let K be the kernel of this action. Kernel or of this representation. So when we will be studying representation theory, then you can find similarities of this theorem. So yeah, maybe this is a good introduction for that part also. Now K is normal in capital G, right? Because you know that the kernel of a group homomorphism is always normal, and K, K is a subgroup of stabilizer of GH, right? As this part is clear.
So why it is a subgroup of stabilizer of G?
Yeah, because K is K is kernel of this homomorphism. That means yeah, let me write it. So the elements of capital K are the small k of G such that K of G1H should be G1H, right?
Yes, sir.
Yeah. So now, and that is for all G1 H of G by H. So take G1 equals to E, G, then you will see that K dot H is H, right? So that is why you can see that we have written there, and that is also for all small k, capital K, and by this we mean that G, which is nothing but G of H. Now clear?
Yes, sir.
Yeah. Okay. So now by the first isomorphism theorem, we have injective group homomorphism that is induced from lambda, obviously, G by K to G by H, because K was kernel of this morphism. So this is true. Now you know that cardinality of a permutation group of n elements is n factorial, right? That is S is n factorial. So we have the index of K in G is less than equals to n factorial. So you have seen that like a pretty complex and pretty abstract question can be solved easily when you tackle it with group actions. I mean, this is quite interesting from this angle if you see, or check after the class carefully the notes. Now what we will do is yeah, maybe we should do this. So you know what is called a center of a group, right? That means the collection of all the elements which commutes with every element. Okay, I will write it down clearly. So this was question number 6. So yeah, question number 7. Let G be a group if center of G has index n, prove that every conjugacy class has at most n elements. So let us clarify some notations first. So ZG is nothing but, okay, the center of G is nothing but x of G such that x dot G is to G dot x for all G belongs to G. And by conjugacy class, you obviously you know that G for x, the conjugacy class of x is G inverse xg or gx G inverse. I mean, if you treat conjugacy class as the equivalence classes, equivalence relation, then equivalence classes are conjugacy classes. So maybe you should think this for 2 or 3 minutes, then we can again talk about this. আরে দাদা হ্যাঁ হ্যাঁ কেন এটা তো কমপ্লিট খাই দিচ্ছিস
থ্যাংক ইউ।
এটা ওই ওয়াল হ্যাঙ্গিং টাইপ,
তো এগুলোই ভালো লাগে।
সেই জন্যই নিলাম।
থ্যাংক ইউ। তবে আমি আরেকটা গিফট দিচ্ছি।
হ্যাঁ, আমি চকলেট খাই না,
চলে না চিকি।
আমি চিকিও খাই না। আমি
ভালো খেতে।
আমি জানি আমার আমি সেই রুমে রেখে দিয়েছিলাম,
হ্যাঁ।
পিঁপড়ে লেগে গেছিল। মানে
খেয়ে দেখতে হবে।
আরে আরে
খেয়ে
চিকেন
কি করবো যখন জোর করে দিচ্ছি।
কিন্তু তোমরা ইয়ে খাও একটু, মানে আমি নাহলে খাই না মিষ্টি, মানে
কিন্তু আলাদাই জিনিস এনেছিস, আমি তো তোকে এত জিনিস জিনিস দিয়েছি। ঠিক আছে, এরা আমি পড়াচ্ছি। আচ্ছা, আইপিএল পড়াচ্ছি আমি পড়া
বুঝলি। আমি
এইটুকু।
আমি নিয়ে
তুমি দিয়েছো বলে না করতে পারলাম না।
টাটা।
থ্যাংক ইউ। ছেলেটা কত ভেবেছিতে গিফট দিয়েছে। এগুলো কেন এত ভালোবাসে?
তোরা চুপ কর। So one thing is clear that right that okay, let me write it. So under the action of G on itself by conjugacy, we can see that the center of G is a subset of stabilizer of Gx for all x belongs to G, right? Because from here it is clear that G inverse xg equals to x, right? So now any x you take from your zg and you see that G inverse xg equals to x for all G belongs to G. So oh, sorry, you can just write it like this also. G should be x inverse gx. Then it makes sense, right? Yeah. Then it makes sense. But there may be some notational complications. But yeah, the overall statement makes sense. Now from the index theorem, or you can say the transition property of the index theorem, index of a subgroup, you can you know this, right? That g of this dot gx or center of g, this should be equals to z g, right? So now we use that orbit stabilizer theorem. So by the orbit stabilizer theorem, we have that gx equals to x. So in particular, the number of elements in is conjugacy class is at most n. So you can see that the original problem was that if zg has index n, that means this was your n. Right? So now can you make sense of this? Can anyone tell me?
Yes, sir.
Yeah, okay. There are some problems involving dihedral group, permutation group, that I have prepared for those, but as those will be monotonous, so I am focusing on like trick based questions. Those are also like trick based question, but those are very hard computation, and from my experience from the previous class, I am trying to avoid those which involve like very hard computations. So I encourage you to like try those and maybe discuss among yourselves, and maybe uh, if you have some doubt, you can send me directly so that I can also look into them. Okay.
Okay, sir.
Okay. So okay. Uh, Now we can do one or two problems and we'll call it a night. Okay. Let G be a finite group and P a prime number. Prove that if okay, prove that if capital P belongs to silo small p G, and P is a subgroup of H, and H is a subgroup of G, then P belongs to silo small ph. So I hope you know what is a silo silo p group. That means of a finite group, obviously. So that means it is a p. The subgroup has cardinality of p power, and such that uh, it is not a subgroup of any other p power group. The formal definition they are in the notes, but what I'm saying that I mean if P is a P silo group, then here you can see that P is contained in H. Then if H also, if H has cardinality P of alpha, and P has cardinality P of beta, then alpha has to be equals to P beta, and from there you can see that P has to be equals to H. So what I am trying to say is that then the cardinality of H must be of P to the power alpha some R. I can understand if uh, those who are undergraduates here, uh, if silo group is new to you, uh, I don't know what is the syllabus for the next week, but
So what is capital P here?
capital P is a silo P subgroup, nothing.
Or it's okay. Here P is only that P.
Uh,
P be a prime number.
silo small p G is nothing but the subgroups of G, which are P is silo small p subgroup.
Okay. So we have to show here if P is a silo, P belongs to silo subgroup of G,
Huh?
and H is subgroup of G. Then P will also be a silo subgroup of H
H.
belongs to that. Okay.
So again, this simply comes from the transitivity of the index numbers. So I will just wait for 1 to 2 minutes so that you can try. So in your note, it was called the fixed points of group actions. I think what we have done till now, the kernel of group actions, those are same. I mean, fixed point for the whole set is the whole set A is the kernel of the group action. So we have covered everything that was done in the lecture, and there are some numerical problems related to silo theorems, which are pretty much important in competitive exams along with your syllabus too. but those need some maturity in basic definitions and everything. Okay. Okay, so let us try, and if one of you are done, then you can interrupt me and tell. If P G is a silo P subgroup of G, then small p does not divide the index of H in G, right? I just explained this to you, right? That the power of P in the order of H should be equal to the power of P in the order of capital P. That is the definition of a silo P subgroup. So from here it is followed. Now from the transitivity of the index number, that is the equation G of H and H of P. This also follows from I think this follows from this G by P to G by H. There is a map and the kernel should be H by P. So if this is phi, so kernel of phi should be this, and from here you can use your and this is a surjective map. So using the first isomorphism theorem, you will see that G by P by H by P, their cardinality equals to G by H, and from here it will follow that cardinality of G by P by H by P equals to G by H. So nothing highly non-trivial here. So from here, so that small p does not divide p, right? So can anyone tell me why? I made a mistake.
No, sir, we don't know.
Yeah, so p does not divide this part, right? The left hand side. So I mean, think of this as a number theoretic problem. If p does not divide AB, the product, then p cannot divide A and
Okay.
divide B. This implies this. Because if p either divides A or B, then it should divide PAB. So, and from here again, this is the definition of the silo P subgroup in a group. So your capital P belongs to So capital P belongs to silo small p of H. Now we have just I have just one more problem to discuss. Discuss question 8 and question 9. Let G be a finite group and P be a prime number. Prove that if H is a subgroup of G and Q is a silo P subgroup of H, then again the conjugacy follows, that is G inverse is a silo P subgroup of GH G inverse for all G belongs to G. So you can simply put the equation that you can simply use the result, that is the conjugacy is a automorphism, right? Group automorphism. So the order really does not change of GQ, G inverse and Q. So using that, I think it is easy. So maybe you can try this for 2-3 minutes, and I will just take my time and come back. Can start discussing from 7:45.
এখন mute করে ফেলবো।
Seriously?
হ্যাঁ
He's the best.
পড়া না কটা বাজে এখন
হ্যাঁ? সরে যা আর একটাই প্রবলেম বাকি আছে, করে দিয়ে বেরিয়ে যাচ্ছি। একটু বেঁধে না,
পারবো না
ঠিক আছে, বন্ধ কর। সো how should we start with so one thing to note that note GQ, G inverse is a subgroup of GH, G inverse, and as I said, as conjugation by an element is a group automorphism then small g capital Q small g inverse, its order equals to order of Q, right? And order of GH G inverse equals to order of H. Hence this is clear, right? GH G inverse GQ G inverse, the index of GQ G inverse in GH G inverse equals to order of GH G inverse by order of GQ G inverse, and using this we will be seeing that this nothing but HQ is not divisible by P. So GH plus GQ G inverse is not divisible by P. Right? So GQ G inverse,
Sir,
yeah,
there is little correction.
yeah,
You have written index of Q, third line, sir.
index,
Hence, after hence, hence, and
hence.
then last.
I think I have
So you
yeah.
should have written order of H by order of Q.
Thanks. Yeah. Thank you for correcting. Yeah. Actually, yeah. So is a Silo P subgroup of GH G inverse. So you see that actually to deal with Silo subgroups, the definition is not of much use, right? You cannot tackle problems following definition, so you have to use the equivalent definitions. So one of the equivalent definition is that this thing, and there are one or two more equivalent definitions, but let's see if we can do Silo theorem in the next classes. If there is major change in the syllabus in the next week, then probably you have to do it yourself. And again, please let me know if you have some doubt. And I mean, after this class also fine. Again, I am writing my email here. Uh, this, yeah. So please let me know if you have some doubt, and then if we can solve it together, or yeah. So yeah, we'll meet on the next week, and good night everyone.
Okay, sir.
Okay, good night.
Good night.
Thank you.
Thank you, sir.